Okay, for the third part of homework 7-3, we left off kind of midway through question 8, so I'll go ahead and start by finishing that one up. So we left off, we accomplished part A and B up above. We'd found the time and the horizontal velocity, but now we want to find the work done. Okay, so again, the big thing with the work is the work done on the block, right? We don't want to use the spring force because the spring force is not a constant, right? The force is going to change as the spring's compression changes. So instead, the other relationship here we take advantage of is work is a relation to energy. Okay, so if we can find any change in energy, we can find the amount of work done on that object. Well, the block gains kinetic energy, and so if I want to find the amount of work done on the block, I just need to find out how much kinetic energy it gained. Okay, so initially the block was compressed into the spring, but the block itself was at rest, which means if I'm thinking kinetic energy, if it's at rest, if the velocity is 0, then it's starting with 0 joules of kinetic energy. By the time the block is released, it now has a certain amount of kinetic energy because it now has a certain velocity, which we found from the part before. And so if I want to find the work done, I just need to find really my final kinetic energy minus my initial kinetic energy, which I already know the initial kinetic energy is 0, right, since it started at rest. So really all I need to do to find my work is find my final kinetic energy, which is 1/2 m times velocity squared. Okay, so going back to our measurements, making sure we've got everything. The mass of the block itself was 2 kilograms, and the kinetic energy we found from part C. Okay, so it's just a matter of plugging that in. 1/2 times 2 kilograms times that velocity of 2.82 squared. Okay, and then calculating that number, we should get that to be about 7.95 is what I get. So about 7.95 joules of kinetic energy. Okay, so that's how much energy was gained by the block, and therefore that's how much work had to have been done on the block, right? Since work is just a transfer of energy, that's how much work had to be done on the block. So there's part C. And then part D brings it all kind of to a close by saying find the spring constant. This is something that maybe initially some of us tried with part C. Okay, so initially thinking we know that the spring starts with some potential energy. By the time the block is released, that potential energy has transferred to kinetic energy. So for part D, it really is a simple matter of we start with a certain amount of potential energy in the spring, all of that potential energy transfers to kinetic energy, therefore those two energies have to be equal. So the spring potential energy is represented by 1/2 kx squared, the kinetic energy is represented by 1/2 mv squared, and it's just a matter of solving then for k. They give us all the other measurements. They tell us the distance the spring was compressed was 0.15 meters, it was 15 centimeters. And then our mass again is 2 kilograms and the velocity is 2.82. So we take that, we square that, and then it's just a matter of solving for k. So when I calculate this, I get k to be about 707, it looks like 707 newtons per meters. So 707 newtons per meters when I solve for k. Anyway, okay, so part D, hopefully not too bad, right? As long as we're comfortable with the fact that potential energy of the spring transfers to kinetic energy. Question 9 of homework 7-3 is also mostly a review question at this point. Okay, so it doesn't hurt to come back and think about this though, since we are talking circular motion in the sense that we're talking rotational motion. Okay, so this goes back actually to chapter 6 when we looked at uniform circular motion, but good chance to review. So 1,200 kilogram car is moving on a flat circular track with a radius of 0.50 kilometers. Keep in mind we usually want meters, so I'll go ahead and convert that right now to 500 meters instead of kilometers. The car is traveling at 88 kilometers per hour, and there's going to be one of the biggest issues is anytime we're working with velocity, right, unless I'm just using the constant velocity formula, I want to make sure that this is in meters per second, so I will want to convert that. Question A, what is the centripetal force? Question B, what is the coefficient of kinetic friction for the tires and the road surface? So for part A, the centripetal force is just mass times centripetal acceleration, and we know centripetal acceleration is defined as velocity squared over r, so this is mass times v squared over r. Okay, so they give me the mass of the car, they give me the radius. Again, biggest thing I have to watch out for is I have to convert my 88 kilometers per hour. Got to convert that to meters per second in order to use any type of these force relationships. Okay, so kilometers per hour, converting 1 kilometer to 1,000 meters, and then 1 hour I need to convert to 3,600 seconds. Okay, so just taking this relationship, converting those out, and I should find that this velocity ends up being sorry, I got to turn the page of my homework here. This velocity should be about 24.4 meters per second. So once we convert that to meters per second, we should get somewhere in the ballpark of 24.4 meters per second. Okay, so now that I've got that as my velocity, I can just plug that in with the other measurements. So now if I'm looking for centripetal force, it is just mass. So it's 1,200 kilograms times 24.4 squared all over the radius, which is 500 meters. Okay. So I've just got that relationship. I can set that up, calculate that, and I get that to be about 1,429 newtons. Okay. So about 1,429 newtons of force is what's holding us in centripetally. Part B, what is the coefficient of kinetic friction for the tires and the road surface? So question B is more of the concept relationship. The formula we're going to work with is actually pretty easy, right? The only real formula we work with involving the coefficient of friction is friction equals my coefficient times the normal force. Well, finding the normal force on a flat road isn't that bad. The normal force would have to equal the force due to gravity, and so the normal force would have to equal my 1,200 kilograms times 9.8, since it is a level surface, and we know that the normal force has to be resisting that force due to gravity. Okay, so I know my normal force could be calculated pretty easily using those measurements. So the real question here is, if I need my mu of s, how do I find friction? Well, that's where the concept comes into play. Right? If we're moving around on a circular track, we know that we have to have a centripetal force. But keep in mind, centripetal force doesn't exist on its own. Right? So as I'm moving around in a circular track, I've got to have that force that's pointing towards the center of the circle. But that force has to come from somewhere. And in this case, the only force that's acting in the direction towards the center of the circle, the only force that's actually providing that is friction. Okay, so regardless of whether they asked us for it or not for question A, we actually found the frictional force the second I found the centripetal force. Okay, so my frictional force is what's providing my centripetal force. So therefore, I know my frictional force is 1429. Okay, so plugging that into this equation, I know 1429 equals my mu of s times 1,200 times 9.8. So then it's just a matter of solving for, again, my coefficient of static friction, my mu of s, so solving for that. And if I calculate this, I find that to be about 0.122. Okay, so the coefficient for static friction that prevents us from slipping there is 0.122. Okay, no units on that, right? Anyway, so then our last question in this third homework assignment is a ladder question, right? And I know sometimes the ladder questions can be kind of tricky, but obviously if you approach this, as long as you get pretty comfortable with it, about the same approach every time we see one of these. So in this case, that's not a very good one. Let me just cheat a little bit and use a straight line. That'll make my life easier. Okay, so I've got a uniform 225 Newton ladder leaning against a smooth wall. Smooth tells me there's no friction at the top of the wall. Okay, so here's the wall. I know there's not going to be any frictional force acting up here, which does simplify. The ladder, the total length of the ladder is 9 meters, right? So I know that entire distance is 9 meters. It makes an angle of 78 degrees with the deck. 65 kilogram Bengal tiger rests on one of the rungs that's 3 meters from the top end. Okay, so naturally we put a tiger on this ladder, and he's 3 meters from the top. Okay, so 3 meters down from the top, that's where we've got our tiger. He's got some ears, he's got a tail, he's got a body or something. Anyway, okay, so there's my tiger resting on the ladder. Clearly it's a tiger. So anyway, so they give us most of the distance measurements, right? They give us his weight, they give us his mass, so we can also pretty easily find his weight. And then the other big concept here is if it's a uniform ladder, right? If it's a uniform 225 Newton ladder, we know that that force to gravity has to be acting from the exact center of gravity of that object. So that force of gravity has to be acting exactly 4.5 meters up the ladder. It's got to be acting halfway up there. Okay, so 225 newtons pull straight down, and it's acting at that halfway point. Okay, so we've got that force of gravity pulling down. We would also have the force of gravity of the Bengal tiger pulling down. Okay, so then for these type of problems, it's always good to go ahead and identify all of the other forces involved. So part A asks us to find the force of friction exerted by the deck on the bottom of the ladder, so by the ground on the bottom of the ladder. So we're looking for what's the friction down here. And then part B, what's the upward force exerted by the ladder. Okay, this one's actually probably misworded. It should rather read, what's the upward force exerted on the ladder by the ground. Okay, so really what I want us to find for this question is, what's the normal force exerted upward from the ground, right? We know if the ladder is not moving up or down, the net force has to be balanced out, and since I've got these two forces of gravity pulling down, I have to have a normal force pushing upward, otherwise that ladder would accelerate downward because I would only have these downward forces. Okay, so that helps me to identify maybe a couple other forces down here at the bottom of the ladder. There's one other force we have to keep in mind. Okay, and if at this point we just look at the forces, if we look at our vertical forces, again, those three vertical forces, our two forces of gravity and my normal force, are going to have to balance out. But horizontally, if friction was the only force acting, we'd be accelerating to the right. We know that the ladder isn't accelerating that way, which means I have to have a force exerted to the left, and that force is happening up here, right at the top of the wall. Okay, so that's the force, that's really the normal force of the wall, but that's the force exerted backwards from the wall. Okay, so now that we've identified all the forces, again, part B is actually the easier part right here. If I want you to find the normal force exerted by the ladder, I don't need to involve torque. Okay, so I'm actually going to go ahead and start with part B. If I ask you to find the normal force exerted on the ladder, the only thing we have to recognize is that our net vertical forces, the sum of our total vertical forces, has to equal 0. So the normal force pushing up has to equal the force of gravity of both the ladder and the tiger pulling down. Okay, so we've got our force of gravity of the ladder, which is 225 newtons, plus the force of gravity of the tiger, which again would be 65 times 9.8. Okay, so actually to find the normal force in this case is pretty easy. The normal force at the base of the ladder would be, calculating that to be about 862 newtons. Okay, so about 862 newtons. So finding normal force, not too bad. Now, if there was friction up here at the wall, that would completely change this game, right? If there was friction at the wall, if the friction was pushing up, then we'd have the normal force plus friction equals 862. And we'd have to worry about how much help does friction provide. Okay, but in this case, it's a smooth wall, so I don't have to mess with that. Okay, so it simplifies the nature just a little bit here. Okay. And then part A would ask us to find the force of friction. That's where, unfortunately, if you look at your horizontal forces, you know that the sum of your horizontal forces has to be 0, which tells me that friction needs to equal the normal force of the wall. But the problem here is I don't know either friction or the normal force of the wall. Okay, and unfortunately they don't give me a coefficient of friction. If they did, I could just try and do something like this, right? I could take my coefficient times the normal force that I just found, and I could find friction. But unfortunately, they don't give us that coefficient, so that kind of throws that out the window. Okay, so instead what we're going to have to do is get a little bit more creative, right? And we'll have to use torque. So we can use torque to help us out. Okay, so then again, the idea here is I want to use torque to help me simplify this problem. Okay, and so if I choose the axis of rotation to be the bottom of the ladder, that will greatly simplify this problem because it will mean that the force due to friction and the normal force aren't going to produce any torque. Okay, by having those two act at the axis of rotation, they won't produce any torque. So now if I look at torque, there's only 3 forces that produce a torque on this ladder. Okay, so if I redraw this ladder with the axis of rotation down here, the only forces that are going to produce torque are going to be the force of gravity of the ladder, the force of gravity of the tiger, and the normal force of the wall pushing back. Okay, so then the biggest question becomes, what's the angle involved, right? Well, the angle that they give us is 78 degrees. If this angle is 78 degrees down here, that angle down there is 78 degrees, that means this angle up here would also be 78 degrees, since they're alternate interior angles there. And then these two angles, on the other hand, would have to be the complement of 78 degrees, so each of these angles would be 12 degrees. So then it's just a matter of setting up the torque relationship between these. Well, the torque caused from the ladder itself plus the torque caused by the tiger would have to equal torque caused by the wall. Okay, so there's our relationship right there. Torque of the wall equals torque of the ladder plus torque of the tiger. We know that torque is the force times the angle times sine of the angle and then times the radius. So this would be the force of the wall times the radius times sine of 78 degrees for the wall. This would be the force of the ladder, force of gravity of the ladder, times the radius times sine of 12, plus the force of gravity of the tiger times the radius times sine of 12. And at this point, it's just a matter of plugging everything in. The only measurement that we don't know is the force of the wall, which is also my force due to friction. When you calculate this, you should get that to be about 114.1